Binary logistic regression with one continuous predictor or one categorical predictor in JAMOVI. Binary logistic regression with a continuous predictor in JAMOVI. Binary logistic regression is a statistical method that can be used to find a relationship or association between two variables. One of the variable is the outcome, or it is called a response variable or the dependent variable. This outcome variable have to be binary. Binary variable have only two levels in it. Have the diabetes, no diabetes, heart diseases, no heart diseases, yes or no, smokes, doesn't smoke. The second variable is the predictor, or alternatively it is called the explanatory factor or variable, the independent variable or the exposure variable. The main reason to use this test is to find out whether there is association between predictor and outcome, and whether the predictor can predict the outcome, and whether the variation in the outcome can be explained by the predictor. The predictor can be a continuous variable, can be binary variable, can be a multinomial variable, or it can be ordinal variable. Continuous predictor is a variable that have a scale data in it, measured at either an interval or a ratio level. Here in JAMOVI data sheet, I had inserted two variables. The first one is the age, the second one is the heart diseases. There are 100 cases in this data sheet. So here we have two variables. The first variable is age, and it is a continuous variable. It's measured at a scale. And a second variable, which is the heart diseases, is a binary variable or binomial variable, as it has only two levels in it, whether you have the heart diseases or no heart diseases. To find out whether there is association between age or increasing age with the probability or the possibility of having heart diseases, then the binary logistic regression can be used, as the outcome here, which is the heart diseases, is binary, and the predictor, which is the age, is a continuous. Before we proceed to the test, let's look at some descriptive statistics by clicking on exploration, then descriptive. In this window, drag the age into the variable section and the heart diseases into the variable section. As shown here, I'm going to trim some of the things here, like I don't want the median, the mean, and I don't want the standard deviation. As shown here in this table, there are 100 cases, no missing values. If I click on the frequency table or tables, again a second table is generated. So in the first table, the age has a minimum value of 18 years old and a maximum age of 94 years old. For the second table, which is the heart diseases, there are 44% of the cases have no heart diseases and 56 have heart diseases. To find out whether the age can predict the heart diseases, we will do a binary logistic regression, as the criteria or the condition is set for that test. To do that, click on regression here, scroll down to two outcomes, binomial, and in this new window here for binomial or binary logistic regression, drag the age, which is a predictor, into the covariate section, and the outcome, which is the heart diseases, into the dependent variable. Spontaneously, a few tables are generated, but let's scroll down here and see if we need to select any of these options here. For the reference level, no heart diseases is set at a reference level, or we can swap it to set the reference category as heart disease, but here we'll stick with no heart diseases. For the option of assumption check, we'll not look at it at this stage. Model fits, I'm going to tick on the Cox Snell R Square and also the other one for R Square here. For a model coefficient, definitely we'll look at the odds ratio to generate an odd ratio as shown here. We will give it also a confidence interval for that odds ratio. We'll not at this stage look at these. For the estimate marginal, nothing to select from. For prediction, let's go for classification table. And finally, for save, we'll stick what we have in the output. Again, as shown here, from the output for the binomial logistic regression in JAMOVI, multiple tables are generated. The first table here is the model fit measures. We're going to look at this R square here. This R square, which is equal to 0.774, indicates, or it means that 77.4% of that variation in the outcome, which is heart diseases, can be explained by the age predictor. So there is association between the age and the heart diseases or the outcome. Moving to the second section here as shown in this table, it is the model coefficient heart disease. We will ignore the intercept value, but we will look at the age values. Here is the estimate for coefficient. Here is the standard error, the z-score, the p-value, the odds ratio or exponential b, and the 95% confidence interval. And a footnote is produced here, represent odd ratio versus no. So it is the odds, log odds ratio of heart diseases to no heart diseases. From the p-value here, it shows that there is a significant association between the age predictor and the outcome, which is the heart diseases. This is also confirmed by the 95% confidence interval for the odds ratio, in which the 1.2 fit within the upper and lower limit. So to start with, there is a relationship between age and heart diseases, or chances or likelihood of having heart diseases. The way to interpret this table is that for each unit of age, which is 1 year, there is an increased odds of 1.2 of having heart diseases, and this association is significant. In another way, for every year increase in age, there is a 20% chances of having heart diseases. 20% is calculated by subtracting from 1.21, and that will end up in 0.2. Multiply that by 100, so it is 20%. So there is, from this table, there is an increased chance of developing heart diseases with increased age. So age is a factor that can predict or explain the variation in the outcome, which is the heart diseases. So this is the way to perform binary logistic regression with a predictor that is continuous in JAMOVI. Binary logistic regression with categorical predictor in JAMOVI. Here in JAMOVI datasheet, I had inserted 200 cases as shown in this window. There are two variables. The first one is smoking, and the second one is cancer. So the smoking variable is categorical variable, as it has 4 levels in it. The first level is non-smoker, the second level is smoking cigar, the third level is the smoking pipe, the fourth level is smoking cigarette. So there are 4 categories in this variable. So it is categorical variable or multinomial variable or nominal variable. It's all the same meaning. The second variable, which is cancer, is binary or binomial because it has only 2 levels in it, either yes or no, whether they have the cancer or no cancer. So here we have an outcome which is binary, cancer, and a predictor which is multinomial, which is smoking. To find out whether there is association between smoking and possibility or probability or likelihood or chances of developing cancer, then binary logistic regression can be performed. The test depends on the outcome that have to be binary, and the condition is satisfied here. So we have outcome which is binary and a predictor which is categorical. Before we proceed and do the binary regression, let's look at some descriptive statistics by clicking on the exploration here and then tick on descriptive. In the new window here, drag the smoking to the variable section or variable sections and the cancer to the same box, and then tick on the frequency tables here. And for statistics, since we have both variables are made up of or consist of categories, then we don't need the median, we don't need the mean. For the dispersion, we don't need standard deviation, and we'll keep the rest. Looking at the output here in the descriptive, the first table shows that there are 200 cases and no missing cases in both variable. For smoking, the minimum value is 0. 0 is assigned for those who do not smoke, and 3 for those who are in the last category, which is cigarette smoking. So 0 for no smoking, 1 for cigar smoking, 2 for pipe smoking, and 3 for cigarette smoking. The second table shows the frequencies. There are 50 cases in each category for the smoking habit. For the third table, it shows the frequencies of cancer. There are 100 cases of cancer, and there are another 100 of cases of not having cancer. To find out whether there is association between smoking and cancer, then we need to do binary logistic regression. To do that, click on regression here and then scroll down to the 2 outcome binomial regression test. In the new window here, drag the cancer, which is the outcome, into the dependent variable. Drag the smoking, since it is categories, drag it into the factors since it has 4 levels in it. There are few options to select from here. Model builder, no need to select anything. For reference levels, since we have here 2 categorical variables, the cancer and the smoking, the reference category will be used is the no, those who do not have cancer. So comparison will be to the individual with no cancer. For smoking, there are 4 levels. We can select any of these as a reference group to compare to. We'll stick with the non-smoker as a reference group. Assumption check or checks, not look at it at this stage. For model fit, tick on the Cox Snells and tick on the next one for R square. And for a model coefficient, select the odds ratio here and the 95% confidence interval. For the estimated marginal mean, no selection. For the prediction, again, probably classification table, but we'll not look at it at this stage. Looking at the output from the binary or binomial logistic regression test, there are multiple tables produced. The first table is for the model fit measures. Looking at this value here, which is the R square, it shows that 11.7% of the variation in the outcome can be explained by smoking habit, whether you are a smoker or non-smoker, smoking cigar, cigarette, and pipe. So 11.7% of the variation can be explained, variation in the outcome, which is possibility of getting cancer, can be explained by smoking. Moving to the second table, which is a very important table for model coefficient with the outcome, which is cancer. Again, predictor here is given. Intercept, we will not talk about intercept in this section. For smoking, there are 3 categories. All of them has been compared to non-smoker. So cigar is compared to non-smoker, pipe is to non-smoker, and cigarette to non-smoker. Looking at the footnotes here, those who have cancer given yes, and those who have no cancer, no. So cancer, here we are looking at possibility of developing cancer. The estimate is given for each output, which is the coefficient, the standard error, z-score, the p-value, the odds ratio, and 95% confidence interval for the odds ratio. Here we have 2 levels of significance to check the significance, the p-value and the 95% confidence interval. P-value will be set at less than 0.05, and anything less than 0.05, then this is significant. Here is shown that all the 3 categories, there is a significant association between smoking and developing cancer. And for the 95% confidence interval, all the odds ratio fit within the lower and the upper limit for the confidence interval. So from this table, there is a significant association between the predictor and the outcome. The way to interpret this table is that those who smoke cigar have an increased odds of 2.7 compared to non-smoker. Or in another way, those who smoke cigar have a higher chances of developing cancer, or more likely to develop cancer. For the second category, which is pipe compared to non-smoker, those who smoke pipe have an increased odds of 2.5 compared to non-smoker. So smoking pipe increases the probability of developing cancer. For cigarette category, those who smoke cigarette have the highest likely of developing cancer compared to non-smoker, as the odds is 6. So there is an increased chances or increased likelihood of developing cancer with smoking any type of tobacco here. Those who smoke cigarette have the highest chances of developing cancer. So this is the way to perform binary logistic regression with an outcome that is binary and a predictor that is categorical in JAMOVI. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, JAMOVI, R Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, JAMOVI, R Statistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.